Hey there, and welcome to the Artisirostech Virtual Creative Factory. Listen, if you're watching this explainer, consider it your official onboarding session. I'm going to be walking you through the exact architecture we use out there on the floor of our digital design hubs. Now, as a new developer on the team, you need to understand something right off the bat. We aren't just sending simple text prompts to an API and crossing our fingers. Absolutely not. We are systems architects here. Our absolute mandate is building production-grade, highly reliable autonomous agents that actually drive our creative and industrial pipelines. So by the end of this session, you're going to know exactly how to structure your Python scripts to hit that required level of reliability. You're going to see exactly how we bridge theoretical AI with hard industrial execution. You know, when you play around with standard AI in a web browser, it's designed to be conversational, right? It wants to chat with you. But here in our environment, that chatty behavior translates straight into creative drift and unpredictable conversational filler. Think about what actually happens if an agent replies, "Sure, I'd be happy to update the inventory for you," and then provides the data. Well, because it added that polite little intro before the bracket, the JSON parser reading that output completely fails. And bam, our downstream databases crash. A whole entire pipeline stalls just because the model wanted to be polite. No way. Production-grade agents require deterministic precision and strict, structured JSON outputs. That's the exact level of control we're building today. Okay, let's dive right into this. We use a strict 5-step blueprint for training our models with the official google-genai SDK. First, we'll hit anchoring identity and memory. Second, enforcing deterministic agent output. Third, equipping external agent senses. Fourth, building the fallback loop. And finally, we wrap up with the complete production-grade blueprint. Let's start with step 1 of our Python implementation. Section 1, anchoring identity and memory. Before an agent can do any real work on the floor, we have to give it a stable persona and a vast working memory, so it actually understands the context of the factory. To do this, we leverage the Gemini engine's massive 2 million token context window. Think of this as an absolutely elite working memory for your agent. Look, in standard applications, developers are constantly having to re-inject context into their prompts just to remind the AI what they're talking about, because the window is too small. But with a 2 million token window, the agent retains vast amounts of project history, external data, and prior design iterations across multiple turns without ever needing a refresher. On the Python side, to put that into perspective, you can literally pass massive arrays of previous chat history, entire project code bases, or gigabytes of raw factory logs directly into the contents array. And the model won't lose the thread. It remembers the entire state of the project from start to finish. It's a real game changer. But here's the thing. Memory isn't enough on its own. The agent needs to know who it is. And that is exactly where system instructions come in. These aren't just polite suggestions. They are strict identity anchors deeply embedded right into the agent's reasoning process. When you configure your agent in Python, you inject this directly into the system instruction parameter of the client initialization, meaning it's processed and locked in before the user's prompt is even looked at. You're going to use these system instructions to assign it a specialized, totally unshakable role, something like asset librarian or factory operations agent. This persistent identity framework literally prevents the agent from drifting off task. It ensures its behavior stays strictly aligned with our operational goals here at Artisirostech all the time. All right, moving right along to section 2, enforcing deterministic agent output. So now that the agent knows its job and remembers the project context, we really have to tame its output so our factory systems can actually read and process its decisions. This brings us to a completely non-negotiable part of our architecture, Pydantic schemas. This brilliantly solves that whole conversational filler problem I mentioned earlier. In your code, you're going to define a Python class that inherits from Pydantic's base model. Inside that class, you define your exact fields. We're talking strings, integers, nested lists, whatever the downstream database requires. Then you pass that schema directly into the response schema parameter of the generate content config. By doing this, we create physical structural guardrails. We are physically forcing the agent to output deterministic, perfectly formatted JSON data. So there are no introductory greetings, no concluding remarks, just the raw structured data we need for automated asset cataloging and reliable metadata extraction. And right alongside those schemas, we have a very strict rule for the model's temperature parameter. On the factory floor, we lock the temperature strictly between 0.1 and 0.2. Now, you might be wondering why so low? Because high temperature equals randomness. And let's be real, randomness destroys automation. Locking the temperature at 0.1 eliminates creative drift and ensures absolute deterministic precision during parameter mapping. Just think about it for a second.
If we set the temperature to point 0.8 while an agent is controlling a beam robotics unit, the model might hallucinate a spatial coordinate just to be creative, and suddenly it's sending a robotic arm crashing into a server rack. No thanks. When the agent is tagging a creative asset or checking inventory or moving physical hardware, we need the exact same reliable, predictable output every single time.
For sure. So we have the brain structured. Now let's look at step 3, equipping external agent senses. Because an agent is pretty much useless if it can't actually interact with the physical and digital world of the factory. We connect the agent's internal reasoning to the external world through local tools. You're going to be writing Python functions that act as the agent's actual senses. The standard example we use is inspect factory inventory, which lets the agent fetch real-time data about parts. But we are really pushing the boundaries here. You'll be integrating tools that interface directly with the beam robotics revolution, allowing these agents to monitor and command physical hardware. You'll build bridges to our design workflow automators and enable the agent to query the VCF galleries to pull specific digital assets based on really complex design specs. And the mechanics of this in your code? Fascinating. When the agent decides it needs external data, it actually pauses its generation and returns a function call. Your Python script has to be set up to intercept that call, execute the local beam API or the database query, and then pass that result back to the model as a function response. Only then does the agent resume its reasoning, now using that fresh, real-world data.
All right, let's talk resilience in Section 4, building the fallback loop. Because even with Pydantic guardrails and a low temperature and a complex environment, well, things can occasionally misfire. We absolutely need our agents to be completely self-correcting.
So the crucial point here is exactly how we handle errors. We don't just let the application crash if the agent happens to output malformed JSON. Instead, we implement a multi-turn fallback loop directly in our Python script. In practice, you're going to wrap your generation call in a while loop and a try-except block. Step 1, the model generate content runs. If the parse data somehow violates the schema, the accept block catches the validation error. Step 2, and this is key, instead of just starting over, it takes that exact validation error string and appends it to the chat history as a corrective prompt. It's basically telling the agent, hey, your last output failed because of this specific schema error, fix it based on these rules. Step 3, the loop restarts and retries a generation. We typically allow up to 3 retries here. This self-correcting loop dramatically increases our operational trust because the agent catches and fixes its own mistakes entirely under the hood way before they can corrupt our downstream processing pipelines.
And finally, let's pull it all together in Section 5, the production-grade blueprint. This is really the culmination of everything we've discussed today, unified into one single, powerful architectural approach. When you sit down at your workstation to actually write your code using the google-genai SDK, this is your mandatory checklist. 1. You define your Pydantic schema to strictly enforce clean JSON output. 2. You set your system instructions to anchor the identity and you lock that temperature down to 0.1 to eliminate any hallucination. 3. You attach your local tools, like the beam robotics interfaces or the VCF gallery search, making sure to intercept those function calls so the agent can really see and interact with the real world. And 4, you wrap that entire generation process inside your multi-turn try-except fallback loop to guarantee absolute reliability. This matters, guys, because skipping even one of these steps results in standard, fragile AI that will absolutely break in production. Combining them all, that is exactly how we translate theoretical AI concepts into highly reliable, scalable autonomous enterprise systems right here on the factory floor.
So you now understand the cognitive mechanics. You have the structural guardrails, the identity anchors, and the self-correcting loops. The google-genai SDK is right there waiting for you. Now it's your turn to rate the code. With these production-grade tools at your disposal, bridging advanced AI reasoning with actual real-world robotics and creative pipelines, what incredible autonomous workflow are you going to build next in the virtual creative factory?